Hello everyone and welcome back. What I want to do now is get into annuities, which is really getting to the heart of this course. Okay, so what are annuities? Annuities are just an annuity is just a series of periodic payments. So for example, a mortgage is an annuity. You're making periodic payments to the mortgage company at the end of each month. Paying back a loan is an example of an annuity. You're making payments at the end of each period, however the loan is structured, to pay off your debt. So in general, there's two types of annuities. First one that we'll talk about in this video is an annuity immediate. And so in this situation, all payments are equal. Payments are made at the end of each period. And payments are based on a constant interest rate compounded at the same frequency that payments are made. Okay, so an example of an annuity immediate are typical loans like student loans or mortgages. Okay. And I mentioned, usually you make equal payments at the end of each month for a mortgage or at the end of each period for your typical loan. And we'll get more into how loans and mortgages work. But the other type of annuity is an annuity due, and it's the same thing, but payments are made at the beginning of each period. So very typically, this would be like making rent payments, where let's say you make payments to your landlord. Okay? Your landlord's gonna be pretty upset if you make payments at the end of each period. Okay? So in this example, where would compound interest come into play? Well, just imagine if you make payments to your landlord, and your landlord then deposits, immediately after payment is made, deposits this amount in a bank account. Okay. So what we want to do now in a situation like I just described, but for an annuity immediate, we want to see what the accumulated value of such an annuity is based on an interest per period rate of J. So in this time diagram, we have N periods. We're making payments of P, or if you like, deposits of P into some account at the end of each period. As I mentioned, interest rate per period is J, and we want to see what the accumulated amount is. So the situation, practically, this could be you're a mortgage company, you're taking in payments of P at the end of each month. Right when you get those payments, you invest it into some account earning J per period, okay? Or J per month in the case of a mortgage. At the end of maybe 30 years, 360 months, how much do you have based on depositing this amount at the end of each month and letting it accrue interest? Let's see. So at the end of the first period, you deposit P, all right, and that sits in this account for N-1 periods. The per period interest is J, so this becomes P1 plus J to the N-1. At the end of the second period, we make another payment into this account. This sits in the account for N-2 periods. So that's going to become P1 plus J to the N-2. And let's just keep playing this game, and let's look at the last two payments or deposits. So we make the second to last payment, deposit into this account. That accrues one period of interest. And the last payment into this account does not accrue any interest. We're making this payment
at the end of the nth period, we're looking at the accumulated value of this account based on all these payments at the end of the nth period. So this payment here accrues no interest at all. So just like we've done in previous examples, to get the accumulated value, we just add up all these accumulated values corresponding to each of these individual deposits or payments into this account. All right, so we do all that. Let's factor out P. All right, so in this, in this loan or this mortgage example, N could typically be 360 or in 100. So for example, if you have a 30-year mortgage, each year there's 12 months, so that's 360 months. If the mortgage company does exactly what I said, whenever the mortgage company gets a mortgage payment, it immediately puts it into this account, earning J interest rate per period. Then, to figure out what the accumulated value would be in this account based on all these payments at the end of 30 years, you have 360, terms add up. That's unreasonable. So we have to use a finite geometric series formula, like we've already done. So in particular, my R is going to be 1 plus J. So it's going to be 1 minus R to the highest exponent plus 1. So it's n minus 1 plus 1 is n, over 1 minus R. And I said again, as I said before, rather, R is 1 plus J. So I want to simplify this a little bit because the denominator is going to be, well, distribute, the minus, and it becomes 1 minus 1 plus minus J, and that's going to be minus J. And that's kind of a pain to have a minus in a denominator. So to multiply the top and bottom by minus 1, the bottom becomes minus J is J. If you minus the top, it becomes a minus 1, and this minus here becomes positive. Okay? So we have this nice formula that the accumulated value of an annuity immediate with payments P at the end of each period with a per period interest rate of J. And if we do this for n periods, then the accumulated value is P1 plus J to the n minus 1 over J. And we're going to use this formula so often that we want a nice shorthand notation for this term right here. And so we're going to use SNJ for that shorthand notation. Now, I don't really want to comment on this notation here. It is bizarre. It is weird. It's almost like some alien symbol. But this is absolutely standard actuarial notation. It is absolutely notation that will be in your future courses and on Exam FM. So I'm definitely going to use it. And you'll definitely get used to it. You're not going to really, frankly, have a choice because you'll do so many problems. We'll do so many examples that you're going to get used to it. Don't worry, even if it is very weird looking. Okay, and this has a nice interpretation as the accumulated value of the annuity immediate, where we deposit $1 at the end of each period for n periods at a per period interest rate of J. Why does it have that interpretation? Well, set P to be 1. Okay. So if we make $1 payments at the end of each period, well, we get exactly what we have here, where there's essentially no P's, because P's, by no P's, I mean P equals 1. So we're multiplying everything by 1. So I shouldn't say there's no P here. P is 1. It's just kind of the P's go away here, but here P equals 1. So anyway.
And so in summary, we have the formula, the accumulated value of an annuity immediate, payments P at the end of each period, and periods per period interest rate of J as P, S, and J. All right. So let me immediately dive into an example. So we have level payments, or level deposits rather, on May 1st and November 1st each year from 2013 to 2020. And we want that to accumulate to $7,000 on November 1st, 2020. And we want this to happen if we have an interest rate, a nominal semi-annual interest rate of 9%. What do these level deposits have to be? So first of all, level means constant, okay? All right, so let me draw a timeline to illustrate what's going on here. So I should mention between May 1st and November 1st is 6 months, and likewise between November 1st and May 1st is 6 months. So these are 6-month periods. And I should also mention that very often interest rates are given in real life as nominal, usually in real life, when you're dealing with annuity immediates like mortgages. Interest is given at a nominal interest rate because they're just very natural. It's very natural to do that, as we'll see when you're doing annuity calculations. Nominal interest is very natural when doing annuity calculations. All right, so let me go to the whiteboard to do this. Okay, so yeah, let me just draw a timeline. So the first payment of P is May 1st, 2013. Okay, so 6 months later, we make another deposit of P into this account. So we're in the same year, November 1st, the same year as May 1st. And I'll write down one more. So November 1st to May 1st, we're going to the next year. Yeah, I don't know why I wrote Moy. It's May. Anyway. Sorry, May 1st. Okay, and we keep doing this. I'll make the dots a little closer to the end. So we keep doing this until we hit the very last one, and we're given that's on May 1st. I probably should put commas here. Looks a little neater. So it's May 1st, 2020. So you'll notice that this is not exactly the timeline that corresponds to our annuity immediate situation. So in our annuity immediate situation, sorry about that. Computer kind of went a little weird there for a moment. Okay, so in our annuity immediate situation, we start off at a certain time, and one period after that is when payments or deposits, whatever, start. So we can fix this situation very easily. All right, so all we do is, well, we just go back, and that's why I gave myself some room here. And we just start this timeline 6 months prior to May 1st, which is November 1st. To kind of squeeze this in. So it's November 1st, 2012. Okay, so now we're in exactly the annuity immediate situation here. Okay. So it might be clear that this is going to correspond to 16 6-month periods. If it isn't, let's just see the pattern here. So November 1st, 2012 to November 1st, 2013 corresponds to 2 6-month periods. Okay, so that corresponds to 2 periods, and we just keep going. November 1st, 2013 to November 1st, 2014 is another 2-month period, another 2 periods rather, 2 6-month periods. Sorry about that. Just kind of looked a little weird. Okay, so we keep going. Okay. And you should see the pattern here. So we just keep going here. Maybe I'll do one more. Well, actually, I'll just I'll just finish it up rather than keep going. So what I mean by that is November 1st, 2019 to November 1st, 2020. Well, that's going to therefore correspond to 16 periods. Right? So 12 to 13 is 2 periods, 13 to 14 is 2 periods. So if we're going from 12 to 20, it's 8 times 2 periods, which is 16 periods. Okay, so why is it natural to be given a nominal interest rate? Well, nominal semi-annual interest is 9%. So if you remember what that means is the actual 6-month effective interest rate, meaning the actual 6-month interest rate, is just this number here divided by 2. Okay, so we get our per period interest rate as 0.045. So this is our 6-month interest rate. Okay, so let's use our formula. Okay, and I just want to again emphasize we are in exactly the annuity immediate situation here. The way we set up the timeline, we have 16 payment periods, and at the end of each period, we make a deposit, we make a payment. Okay? And if I didn't mention, I think I did, but if I didn't, P is the payment at the end of each 6 months, and we're trying to figure out, or deposit rather, at the end of each 6 month, each of these 6-month periods, and we're trying to find what P is. We're trying to find what each of these deposits are. Okay, so now we can just plug and chug. So we were given that we want 7,000 at the end of November 1st, 2020. So it's going to be 7,000 equals whatever P is, we don't know what it is, S16.045. Okay, so yeah, so let's just plug into our formula. So so maybe I should have just wrote this on this page, so I'll just write this really quickly. Okay, so this is going to be P, dump it into our formula, 1 plus J 0.045 to the 16 minus 1 over 0.045, which is our J. Make that a little neater. That's good enough. Kind of a pain to write with this pen here, but anyway. Okay, so, right, so now all you do is dump this into your calculator and solve for P, and you're going to get 308 and 11 cents. So at the end of each of these 6-month periods, you're making a deposit of 308 and 11 cents into this account. Okay. Okay. So let's do another example. All right. So in this example, so let's say instead we want an accumulated value of 2,000, and we're still going to make semi-annual deposits of 308.11, which we just found for this problem. And we're going to do this, except to get to 2,000, we're going to make one final smaller semi-annual payment. Let's find the date of this last payment and the amount of this last payment. All right. So I'll draw again the time. Well, actually, maybe it's easier to keep the timeline I have up. I'll draw a new timeline, probably easier. All right, so yeah, let's draw a timeline and then see where we go from here. Okay, so setup is exactly the same as before. We start off at November 1st, 2012. Our first payment of 308.11. So this example should illustrate that you can't really just plug and chug into formulas. You really have to figure out what's going on and figure out how to set it up, set the problem up in such a way that you can plug into formulas. And that's really going to be the heart of this course, figuring out how to set things up to be able to utilize our formulas. I mean, it is a 300 level math course after all, so all right, so yeah, the next one is November 1st, 2013. Okay, and we keep going until we have a payment, a second to last payment of 308.11. And then finally, the last payment of, let's say, X. We don't know what X is, and we want to figure out what X is. And I don't know what this date here is because I don't know when the last 308.11 is going to be. Okay, so we're going to do this similar to the way we did a previous problem a few videos ago, where we don't know when, we don't know how often we're making deposits. I think that was basically how we did a problem like this. So we're going to set up the equation 2,000 equals 308.11 SN 0.045. So we're in the same situation as before, where the actual 6-month interest rate is 0.045. Okay, so we're going to solve for n and then round down to the nearest integer. Okay, So n, when we solve for n, we're not going to get an actual integer because there's just no way to keep doing this, keep making this 308.11 payments and accrue exactly $2,000. There's no way to do that. That's the whole point of this final payment 6 months after the last 308.11 to get to 2,000. Okay. So, right. So this is pretty straightforward. I'm not going to go into details here. Solving for n. At this point, if you can't solve for n, you are definitely in some trouble. I'll just write down the equation. 1.045 to the n minus 1 all over 0.045. And this is a 4 here. Sorry about that. Okay. Right. So we have, just to kind of summarize, 2,000 is 308.11. 1.045 to the n minus 1 over 0.045. I mean, of course, you would divide by 308, multiply by 0.045, add 1, take ln's. I mean, so at the very least, when you solve for 1.045, you get 1.29210 is 1.045 to the n. Take natural logs, you get n is ln of 1.29210 over ln of 1.045, and that is going to be 5.822. Okay, so again, what we're going to do is round down to the nearest integer, not round up, round down. So we're going to look at 5 payment periods. So here's the situation here. This is no longer a question mark. This is going to be 5 payment periods. So let me actually just squeeze, didn't want to do that. Okay, so 1, 2, 3, 4, sorry, there's going to be 5 payment periods, 1, 2, 3, 4, 5. So this is going to have to be a little, cram this in here a bit, but, right, so this is going to be May 1st, 2014. This is going to be November 1st, 2014. And this is going to be November to May is May 1st, 2015. And these are all 308.11. Maybe make that a little bigger. Okay. Right, so what we need to do is we're going to figure out how much is in the account at the end of May 1st, 2015. Whatever that amount is, so let's figure out what that amount is. All right. Well, we know what that is. It's just going to be plug into our formula. It's 308.11, 308.11 cents. S5
0.045. And this is going to equal, plug into your formula, 308 and 11 cents times 1.045 to the fifth minus 1 over 0.045. You're going to get 1658 point roughly 58. I'll round to the nearest 0374. Right. Okay, so now here's the slightly tricky part. This amount here is going to accrue 6 months of interest on November 1st, 2015. So this is the accumulated value from the 30811 payments, deposits rather. Yeah, let me just, this is, let me get rid of these here. Yeah, so this accumulates to $1,658.58. Okay, but again, this is going to accumulate 6 months of interest if we want this amount here. So basically, it's like this amount here sits in the bank, in the account for 6 more months. And then on November 1st, 2015, so on November 1st, 2015, and I'm going to write this before the last deposit. How much is in the account? What's the accumulated value of all these 30811 payments? Well, there's really not a whole lot to this here. It's, I'll do it here, 1685.58 times 1.045. And that's going to be equal to $1,761.43. But we want $2,000 on November 1st, 2015. So obviously we have to have 2,000. So 2,000 equals the 1761.43 plus X. So X is going to be equal to 238.57. So the answer, there's 2 answers. First of all, the last payment, the smaller payment, and it is indeed smaller than 30811, is $238.57. Or rather, this last deposit. For now on, I'm using deposit, payment interchangeably, because whenever I say payment, it's implied that someone is taking this payment and depositing it somewhere. Okay? Because like I said, it's realistic that, anytime you have money, you can always deposit it somewhere into some account to earn some interest. So anyway, so yeah, this last payment is $238.57, and it occurs on November 1st, 2015. Okay, so last but not least, it's not really part of this problem, but let's do a check. Let's do a sanity check, and let's actually just check our answer. I think it's very valuable to do that.